In this video, we're reviewing some famous power series. So first, the power series for e to the x, and I'll post a link to where that came from. Second, we're looking at the power series for the sine function. And third, we're looking at the power series for the cosine function, and I'll post a link to where that came from as well. And I noticed something very interesting about these three power series. If I look at the sine function, I end up with only the odd powers of x in that. And this, in fact, is necessary because the sine function has odd symmetry. It can only contain pieces in its power series expansion that also have odd symmetry, which means odd powers of x in this case. The cosine function, it only has the even powers of x, or if I make a symmetry argument, again, I can say the cosine is an even function. So its series has to have terms that are individually even functions. And if I take sine and cosine together, it looks like they have all the pieces that it would take to build e to the x. It's just a matter of how do you fix the minus signs in these alternating series to make it work out so that you get e to the x out of this thing. And you might try plugging in sine of negative x and cosine of negative x and kind of messing around with it. And it just doesn't work until you try something a little more exotic. Let's try evaluating e to the ix, where I is the imaginary unit, or the square root of -1, or the thing you square to get -1, if you want to look at it that way. And when I plug that in, I get 1 plus ix plus I squared x squared over 2 factorial plus I cubed x cubed over 3 factorial. I'm going to go for a while because I want to have a lot of terms to recognize the pattern from. Okay, to simplify this, I'm going to need to write down the values of all these powers of I. I'm just going to do that separately because it's going to make things go a little faster. So I can start with I, and then when I square I get -1 by definition. When I cube I, well, that would be I squared times I, but I squared is -1, so I get negative I. When I raise it to the 4th power, that would be I multiplied by I cubed. But the I squared there is -1, so I end up with +1 again. And after that, we're going to cycle. I to the 5th is I times I to the 4th, or I times 1. So that's I again. I to the 6th is I times I to the 5th, but I to the 5th was I. So I end up with -1. And so on and so on. Plugging all these into my expression for e to the ix, I get 1 plus ix minus, because I squared is -1, x squared over 2 factorial. Then I cubed is -I, so I have another negative term. And then I to the 4th was just 1, so x to the 4th over 4 factorial. I to the 5th is just I. And I to the 6th was -1. If you've had a little bit of experience with complex numbers, one of the first things you would instinctively try to do is gather the real parts and the imaginary parts. So I'm going to gather all the real parts. And something beautiful happens. Hopefully you recognize that. That's exactly what we have over here for the cosine function. And then I'm going to gather the imaginary parts and factor out an I. And that gives me x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Presumably the next one is negative x to the 7th over 7 factorial, and so on. And in those parentheses, I see the power series expansion of the sine function. So we've arrived at one of the most famous formulas in all of mathematics. E to the ix is equal to cosine x plus I sine x. And this is Euler's formula, which allows us to geometrically interpret complex numbers in a powerful way. We don't have time for that right now, but I do want to verify real quick the formula that appears on so many t-shirts and hats relating these three mysterious constants, e, I, and pi. If I replace x with pi, I get cosine pi plus I sine pi, which is 0. And there it is, e to the I pi equals -1. Probably the most popular math t-shirt of all time.